Thanks, Idan, for the nice introduction. As Idan said, my name is Nir. I'm R&D Group Manager at StoreDot's, and I'm going to present to you today topics about our company, our goals, our challenges, and roughly where we are now. I must begin to say that I'm very excited to be here. It's my first electrochemical conference here at Bar Ilan. I actually grew up at Bar Ilan at Professor Orbach lab. He's listening very carefully right now. And it's actually nice to see the electrochemical industry in the last few years, how we have more and more startups and a lot of people from Orbach and Pellet and every electrochemical lab working. And it's nice to see the ASIA in the matter. So, normal. Okay. So I'm going to talk today about our vision and challenges, who are StoreDot's, how are we working, and then later on I'm going to dive a bit into the technology. If I separate this to roughly two sections, the first part are slides that PR wanted me to show, and the last slide are stuff I want to talk about and PR allowed me to show. I will show some results, and sadly I cannot show the material we use because they are proprietary. But they really gave us a jump in our technology. That's what I'm going to show you. So start with our vision. Our vision is actually to create a system where the driving experience, fueling, and range for electric vehicle will be the same as of gasoline. You enter the electric station, charge your car in like 5 minutes, and go out. That is our goal. That's what we are trying to do. And of course, this brings a lot of challenges. Okay. Oh, now I can hear myself. So first, if I define our obstacle, there are actually terms for that. First, we have a range anxiety. And range anxiety is the fear of an electric car to reach its destination. You want to know that you charge your battery enough, and you will get out from your home, you reach where you want to go, and come back. Later, you have the charging anxiety. And charging anxiety is the time spent charging the car. Everyone wants to charge the car very fast, so you won't get stuck in the electric station for a day or something like that. Today it takes several hours to charge fully the car. And where is StoreDot's? StoreDot's is in between the electric vehicle or any car designer and the infrastructure. We are trying to optimize the mile per minute of charging. We are trying to build the entire battery system, the chemistry, the materials, the formulation, the cell design, the pack design, even the BMS, to fit in between these two. And we have partners from both the vehicle companies and both the infrastructure. And why it's important? Because wherever you look, all the analysts say that in a few years from now, more and more demand for lithium battery will be in every transportation method you can see. We saw it in a previous presentation, and we know that the future is shifting to that. Governments are pushing car companies to switch off internal combustion energy and do more and more electric vehicles. They don't want pollution in the city, so more and more car companies are trying to create electric vehicles. And in order to succeed in the market penetration, you need to have enough miles per charging, and you need to have a good range of the battery itself. Maybe you can have a battery that is charging fast, but you won't reach a lot. Or maybe you can drive a lot with that battery, but it will take you longer to charge it. So we are trying to improve it, and you have to have improvement both in the energy density and the charging capabilities. So So let's move to StoreDot overview, who we are. And this is actually the most important thing in our presentation. Why StoreDot's? I want to show you how StoreDot is built and why it's so important that we build this company like that. And StoreDot was founded in 2012. We raised $130 million to date. And we have a multidisciplinary teams of 120 professionals, up and down, sometimes 100, sometimes 120. And I think this is our most important part. This is our strength. Because we have such a multidisciplinary team from organic chemists, material scientists, electrochemists, system designer, an engineer that work all together to bring something from the lab scale up to a product. And we always see in our work how I can do something in coin cell and work perfectly, but when I move to one interface, something totally different. Fix it in one interface, pouch cell, move to multi-interface, something totally different. And this back and forth we have in our company is one of our main advantages. We also have some strong investors and partners, both from the infrastructure to the car manufacturer and even in the cell producing companies. And of course the map of competition is quite large. You can see here a lot of companies that are producing lithium-ion technology, and we are trying to bring the extreme fast charging to the system. Here's a short roadmap of what we did in the past. We managed to create a nice battery. I will talk about it. That's very pricey, sadly, but shows very good charging capabilities. And the way we do it is we look on the system in a holistic approach. We have innovation all across the cell components, the anode, the cathode, the electrolyte, the cell design itself. That's something I was so unaware when I was in the academia and tried to build some cells. And again, things work very nicely in coin cells, but then when you try to make it in a system, in BMS, there was a huge gap. And so we had to even develop ways to run the cells. And it's not the standard charging, discharging you usually show in papers. So when you try to build and bring this product to life, you have to deal with this entire range of challenges, actually, both in the material, then in how you put this material in the battery, how you make it to be stable, how you make it become safe. And to deal with this entire challenges, we build the company in a way that you always have people from a wide range of abilities. We have a very strong organic chemist and synthesis group, where I as an electrochemist can come and tell them, okay, I need a material that is being oxidized at this point, and I want it to create an SCI in this affinity. And they synthesize it to me, and I test it, and back and forth, and back and forth. Then we finish that part, we move it on to the cell design. And we even started to use data science to our entire system, to help with the system integration. And we have an engineer department that has a small pilot plant that actually can produce the cell. And we have even partners that manufacture our cells. And we always have a back and forth to all this range. So today I'm going to talk about a bit about some improvement we made to metalloid and silicon-based anodes. This is our roadmap. We are now, the entire R&D department are trying to bring this to the market or make this a product. It's based on the silicon anode. Previously we worked on germanium-based compounds. I'm going to show some results with that. And I'm going to talk mainly about how this kind of work help us to improve ourselves and to actually reach some targets we have. So if you look on silicon, I think you all know this scheme. Silicon, when you charge it, it expands. When you discharge it, it contracts back. it breaks its contact to the current collector and the entire binder formulation you put on the anode. It creates an unstable SCI. You have a continuous reduction of the electrolyte, and you have a lot of other problems that comes with it. Gas formation, impedance increase, capacity loss, swelling of the cell. We saw that at the beginning, even if you take the silicon anode itself, you charge it, you discharge it, after 70 cycles at our initial electrolyte system, you still twice expanding the anode itself. And that's the discharge rate of the silicon, not talking about the swelling itself. So this was kind of like a starting point where we wanted to protect the anode itself. We had to rethink the electrolyte system and the binder system of our anodes. And this is an example for, we started to work on the electrolyte itself. And we did the same cyclic voltammetry lithium deposition, the solution you do in the lab. We came to the organic group, we told them, okay, this is the electrolyte, it's being reduced at that potential. The production, the reduced products of the SCI forms this and that. Sorry for saying this and that. And we need to improve it. We need the SCI to have a flexible ability to allow lithium conductivity in a very fast way. And we started doing more and more back and forth with them until we managed to, here I'm showing you a very nice deposition dissolution, reversible lithium deposition dissolution. So we took this electrolyte itself, and this was at one point, this was our germanium anodes. And the trick with any metalloid, if you compare it to graphite, why we thought to use it. So all the metalloids have a higher capacity than graphite. Graphite has 370, metalloids have almost 10 times, depends on the metalloid itself. So even if you take the same cell design, but you put an anode that material gives you higher capacity, you can use a thinner anode. A thinner anode enables a fast charging. And this was our original thinking. So this was one formulation we did for the germanium anode. You can see here the capacity. It's good, but it's not that nice. It's better than graphite. We managed to charge it. We charge in a CCCV mode. We give a time limit. In this case, it was a 10C, so this was 6 minutes we did it. And if you're not familiar with the CCCV term, you charge it. First you have a constant current until you reach your safety potential, and then you reach a constant voltage. We want the battery to be as much as possible at the constant current stage, because that's the fast charging itself. And if you look on this, we get roughly 700 milliampere per gram at 5C. The loading of this anode is roughly for commercial graphite, so we know that it can fit for a similar interface. But that was not good enough. It's nice, but not good enough. So then we went and we used the same trick that we did with the electrolyte. Worked on the electrolyte itself. We reached a point where the formulation gave us, no matter what we did and changed it, we reached that. So then we worked on the electrolyte itself. We managed to make it more tuned to the germanium itself. And we managed to increase the rate capability of it. We got a very flat line, a very nice rate capability, most of our charging, and at that time this was one of the fastest anode I've seen. But this is germanium. Germanium is pricey. You won't put it in electric vehicles. You need to make something cheaper. And here comes silicon. So we started working on the silicon with the same knowledge and the same workflows we developed for the germanium itself. And the starting point was again good, but not that good. And We use the same thinking that we did for the electrolyte design. What kind of SCI we need for the silicon? And it's really different than graphite itself. What kind of electrolyte we need? And we managed to, with the electrolyte design, to push it upward. Higher capacity at high loading and a very good rate capability. But this was still not good enough. And after we went back, we said, okay, now we can't like finish with the electrolyte itself. So we went back to the anode itself. We started thinking of the binder itself, what it needs to do. We had to think of the formulation. And this is a very high percent of silicon. We took out the graphite almost totally. And then we reach an anode that looks like this. A very flat line, a very high rate capability, and amazing capacity for the anode. So it's nice, but again, you always need to look about the entire system. What about the cathode itself? As I said, we are also working about the cathode. And when we started, we developed a very nice electrolyte. We tried to do the same rate capability for the cathode at the loading we need to do. In this case, it's roughly 4.5 milliamps per centimeters loading. And you reach this point where we have a side reaction when we increase the rate. It was, for me, for scientifically, it's interesting to see a rate-dependent reactions, but for the company, you need to solve it. So again, we worked to have special additives, worked on the electrolyte itself, work a bit on the cathode formulation, and stabilize its rate capability. And this was something nice, at least from my side. So you think of a rate you want to go, or both cathodes, both the anode, both the electrolyte, and you always walk back and forth to create this. And this is very, very different from the commercial binders and electrolytes you see today. And of course, this is not the end. This is an example for our cell design. As I told you, we always work with our engineering department, with our system department, and they design the final cell. We, in our R&D, run the cell at a low, let's say coin cells and the small pouch cells, and we have our own calculator where we can understand from them what we need to do in the small scale system to run in the same manner as their multi-interface system. And then we plug it, of course, in the calculator. We close the anode, we close the cathode, run it together, and we reach this is a cell that's run at 240 watt-hour per kilogram for the fast charging itself. And still not perfect, of course, but it's one of the best we can find today. But this is still not the end. Even when we will manage to fix this and reach now higher cycles, you still need to deal with something like this. This is a testing protocol for a driving profile. This looks like this, charge and discharge. So our main challenge is to take everything I showed you until now, plug it in together, and work in something like this. I mean, here I will. Thanks a lot.